This is applications of the fundamental theorem of calculus, a little practice on part one of the fundamental theorem of calculus, and then some more applications of the fundamental theorem of calculus part two, dealing with graphs and accumulating area. So the net change is given by the definite integral whose integrand is the rate of change. So if we have the fundamental theorem of calculus part two in context, what we end up seeing is that the change in this this bigger function f, so if little f of t is the rate of change, then when we take the integral from a to b, we get the actual change from time a to time b. So let's do some of these problems. If h of t is the rate of change of the height of a conical pile of sand measured in feet per hour, what does the integral from 0 to 5 of h of t represent? Well, that represents the actual change in height of the pile from t is 0 to 5. And they want this in units, so that would be, the units would be feet. Number 2, if v of t is the velocity of a particle moving along the x-axis measured in feet per second, what does the integral of v of t dt from 3 to 10 represent? Answer in correct units. So this is actually evaluating what we would probably consider to be s of t, or the position. So this is the total change in position, or displacement, of the particle along the x-axis in feet between 3 and 10 seconds. So between t equals 3 and t equals 10 seconds. Number 3, if b of t is the rate of growth of the number of bacteria in a dish measured in number of bacteria per hour, what does the integral from 2 to 6 of b of t dt represent? Question mark. Answer in correct units. So if we have b of t, and this is the rate of growth of the number of bacteria measured in bacteria per hour, the integral is going to be the actual change in the number of bacteria. This is the number of bacteria actually grown in t equals 2 to t equals 6. So it's the number of bacteria actually grown from t equals 2 to t equals 6. Number 4, if v of t is the velocity of a particle moving along the x-axis at time t, and the position x of t is 5 at time 2, A, write an integral expression that represents the position of the particle at t equals 10. So if we want to write an integral expression, we know that the velocity is v of t, and we want to take the integral of that from time 2 to time 10. Now, the reason why we're going to take the integral of that is we know that the integral from 2 to 10 is going to tell us the total change in velocity from time 2 to time 10. So this will give us the net change in velocity from time 2 to time 10. So then all we have to do after that is know where we started. And if we know that we started when time was 2 at 5, we can do 5 plus the integral from 2 to 10 of v of t dt. That gives us the answer for part A. So again, that is 5 is where we started, and then we add the integral from 2 to 10, v of t dt, that gives us the net change. So this is where we start, and then this is the net change, so that gives us where we ended. Part B, write an integral expression that gives the total distance traveled by the particle from time 2 to time 10. Well, in that case, what we have to do is we would have to figure out everywhere that the particle ends up being negative and take the opposite values of that. Or we could use an absolute value, and I'll talk about that in a second. So we have 5 plus, let's just, for example, say that v of t in this problem has a graph that looks something like this. So the velocity is positive, and then it goes negative, and then it goes positive again. And let's just, for example, say that this is at 5 and this is at 8. Well, what I would have to do is I would have to say it's 5 plus the integral from 2 to 5 v of t dt minus the integral 5 to 8 dv or vt dt plus the integral from 8 to 10 of vt dt. But that's a lot of work, and we don't even know where these are. I just made some assumptions that they were at 5 and 8 just so I could show you what was going on. But if I could take the absolute value of this, so if I could take the absolute value of v of t dt, what that would end up doing is everything that was underneath the axis would then turn into being over the x-axis. And so because that's true, then what I could have is I could just take the integral of this absolute value, and then that would work. So the answer for B is from 2 to 10, absolute value of v of t dt. So I take 5, which is where I started, and I add the integral from 2 to 10 of the absolute value v of t dt, and that gives me the total distance that is traveled by the particle. Number 5, if p of t is the rate of growth of the rabbit population, measured in rabbits per year, we're having some highly successful typing here. And there were 100 rabbits in the year 2005. Write an integral expression that represents the rabbit population in 2007. So we're going to assume that 2005 has t equals 0. So we're going to take the integral from 0 to 2, because that would give me from 2005 to 2007. I'm going to do the integral of p of t dt. And then that will give me the net change in the rabbit population from 2005 to 2007. In order to get the actual amount of rabbits that we have in 2007, I have to take the net change and add 100. So that ends up giving me the answer for number 5. All right, now this is a little bit new for us, so we're going to talk about number 10 and 11. The graph of a derivative is shown. If we are given that f of 0 is 2, we should probably put that on our table right away. Now, we want to find the values of f for all of these things. So what's happening is we are accumulating area under f prime, and that is going to influence our f. So if we want to fill in the table at 1, what we're going to do is we're going to find this area, and the area of that is 1/2, except it's underneath the axis. So this actually counts as a decreasing amount on our f of x. So anytime we have area underneath, that accumulated area counts as exactly what we were talking about at the beginning. That's the change in the original function from where we start to where we go. So since we know that f of 0 is 2, if we have the integral from 0 to 1 of f prime, that's going to give us the change from 0 to 1. So the change from 0 to 1 was minus 1/2. So we started at 2, and then we add negative 1/2, so we get 3/2. For this one, we're going to do the exact same thing. We started at 2. We're taking the integral from 0 to 2 of f prime of t dt. And what that's going to do is that's going to tell us the net change that we had from 0 to 2. So this area is an area of 1. So the red area was 1/2, the blue area is 1. So we're subtracting 3/2 from the 2 that we had. So 2 minus 3/2 gives us 1/2. We can continue doing this over and over again. So with number 3, it's 2 plus the integral from 0 to 3 of f prime of t dt. And that is another 1 that we are subtracting. So we've subtracted 1/2, 1, and 1. So we've basically had 2 minus 5/2. So this ends up being negative 1/2. The area from 3 to 4 is another negative 1/2. So I'm taking 2 minus all of this area. So all of this area ended up being 3. So 2 minus 3 is negative 1. So I've accumulated another minus 1/2 on my original function. Number 5, we've added a half back. So that means I'm back to negative 1/2. So I've now added 1/2 back. And then number 6, at x equals 6, I'm adding 1, so I end up with 1/2. If I wanted to graph f of x, I know that I start at 2, then I'm down to 3/2, 1/2, negative 1/2, negative 1, negative 1/2, and 1/2. So my graph looks something like this. I mean, it may not be exactly smooth, but it looks something like this. This makes sense because I'm going in a negative direction until 4, and then I start going in a positive direction after that. So what happens is, as I have negative area, my original function is decreasing, and then as I have positive area that's being added, so to speak, area above the axis, then my function is now increasing again. Number 11, graph of the derivative is shown. Find the following values if g of x is the integral from 1 to x of, oh shoot, this shouldn't say derivative. The graph of f of x is shown. It is a derivative of some other functions, namely it's the derivative of g of x and h of x, but that's beside the point. So find the following values. G of 1, so g of 1 is the integral from 1 to 1 of f of t dt. That's definitely going to be 0. That will never be anything other than 0 because the integral under a point is a line and the area of a line is 0. This is going to be the integral from 1 to 6 of f of t dt. So what we have to do is we have to find the area, and we have to take the signed area in this case. So that's 1/2 minus 1/2. Well, I mean, I guess I could continue. So I have 1/2, and then I'm going to subtract the area of this triangle, which is 8. So I have 1/2 minus 8, and that ends up being negative 7.5, which is the same thing as negative 15/2. Part C, we have h of 1, which is the integral from negative 3 to 1 of f of t dt. And in order to do that, I look at from negative 3 to 1, that looks like a quarter of a circle plus this rectangle. So I have a quarter of a circle plus this rectangle. So the circle has radius 4. So I get 16 pi divided by 4, which is 4 pi. And then I add the area of the rectangle, which is 4. So this is 4 pi plus 4. If we look at h of negative 7, h of negative 7 appears to be the exact same thing in the other direction. So I have this rectangle and this half circle, and what appears to happen is I have the integral from negative 3 to negative 7 of f of t dt, and that looks like it's going to be 4 pi plus 4. However, we have to really be careful because this is actually the same thing as the integral from negative 7 to negative 3's opposite of f of t dt. Because notice that when we have this function, the integral from negative 3 to x, when I put x in, I actually have the smaller number, quote unquote. The number that's further to the left is on top. So I have to use my integral rules and notice that it's the opposite or negative the integral from negative 7 to negative 3. And so since that's the case, the integral from negative 7 to negative 3 is all positive stuff. It's all above the axis. So that means I get 4 pi plus 4 for this integral. but that integral is actually negative. Like I have to put a negative sign. So I'm getting negative 4 pi plus 4. So this is our first case where we're getting a negative answer for things that are above the axis. And that's something that happens when we have this case where we have an integral from, let's say, -3 to -7. We're actually accumulating area backwards. And so that's a little bit complicated, but let's think about what's actually happening is we are having this integral from -3 to -7. If we go back to the original thing that we were talking about, accumulated net change. So if I'm finding the change from -3 to -7 in something, if I'm finding the change from -3 to -7, what's actually happening is if this change is positive, so for example, if I'm changing from -3 to -7 and that's positive, what's happening to my function, if I'm looking at it from left to right, my change from -7 to -3 is actually going to be negative. So it's like actually backwards. So if I'm going from -3 to -7 and all of this area is positive, from -3 to -7, I actually should be going down, since if this area is positive over here, what's happening is as I move from left to right, I'm moving up. But if I'm doing from -3 to -7, that means I'm going to get a negative answer, because if I'm looking at it from right to left, I'm actually going down. Letter E, g of -10. That's the integral of 1 to -10 of f of t dt. So based on what we just learned, if I go from 1 to -10, I have this entire uh, semicircle, which is 8 pi, this entire rectangle, which is 8, plus that triangle. And then we also have this triangle over here, which has area 2, 1/2 times 2 times 2, and that's underneath the axis, so I'm going to subtract it. But again, since I have the integral from 1 to -10, that's equal to the opposite of the integral from -10 to 1 of f of t dt. So everything that I just did is going backwards. So everything that's under the axis, I'm actually going to count as positive, and everything that's over the axis, I'm actually going to count as negative. So whatever I get here, I'm going to have to reverse the answer, or give me the opposite of whatever I get. So this is 8 pi plus 6.5. So I'm going to get the opposite of that. So my answer is negative 8 pi plus 13 halves. That looks terrible. Negative 8 pi plus 13 halves. That looks terrible too, but you're going to have to live with it. Or I could distribute the negative and get negative 8 pi minus 13 halves. Letter F, this is kind of a change up at the end. Well, it's basically putting the ball on a tee for you at the end, because we have the derivative with respect to x of h of x at x equals 4. So notice that this is basically just asking about the fundamental theorem of calculus. So if I have the derivative of h of x, that's the same thing as giving me the original function, and I don't have a chain rule situation, so all I have to do is f of 4, and if I look at f of 4, I get -2. So the answer to that one is -2. Practice for the fundamental theorem of calculus part 1. Just going to crank these out and see how we do. Derivative of the integral is the original function with a chain rule, but we don't have a chain rule in number 1, so it's just x squared plus 2x. Well, we technically do have the chain rule, but derivative of x is 1. Same thing in number 2, so this is 1 over x. In number 3, we are going to have a chain rule, so we're going to have 3 times 3x squared plus 3x. And then we take the derivative of 3x, which is 3. So there's actually a lot of stuff going on. This ends up being 81x squared, because 3x squared is actually 9x squared. So 9x squared times 3 is 27x squared. And then when we multiply that by the 3 on the outside, we get 81x squared. We have 81x squared plus 9x. Number 4, derivative here ends up being, derivative of the integral ends up being the original function again. We replace t with x squared, and then we need to remember the chain rule. So we multiply by the derivative of x squared, which is 2x. In number 5, that has an integral. We don't particularly care that much what it is at this point because we're taking the derivative of the integral, so we just get the function back. So it's 1 over 2 plus e to the x squared. So we just replace t with x squared. Then we have to multiply by 2x. So we get 2x over 2 plus e to the x squared. Finally, number 6, this is one that we have 2 variables here, so we have to kind of break this up. So recall that the integral from 2x to x squared of some function, actually I should put a t in there. So the integral of some function with 2 variables, we can break this up into the integral from 0 to x squared of f of t dt minus the integral from 0 to 2x f of t dt. And the reason why it would be minus 0 to 2x is because I could have the 2x down here. It would be plus the integral from 2x to 0. But since I want the 0 on the bottom and the 2x on top, I'm going to do a minus there. So then what I end up with in this case, in order to solve for this problem, I find these 2 functions. So I do the integral from 0 to x squared of f of t dt minus the integral from 0 to 2x. And recall that I'm doing all of this and taking the derivative at the end. So I use fundamental theorem of calculus. I get 1 over 2 plus e to the x squared times 2x. We did that in the previous problem. Then I'm going to subtract what happens when I have 2x in this case. And the derivative of 2x is just 2. So I get 2 plus e to the 2x in the denominator and 2 in the numerator. It's kind of sloppy handwriting, but sorry about that. 7, 8, 9a, and 9b. Let g of x equal 3, the integral from 3 to x of t cubed dt, find g prime. So that's just the derivative of the integral, which again is the function. This is the fundamental theorem of calculus, that is x third, or x to the third. Number 8, this is once again the fundamental theorem of calculus. So we have tangent cubed of sine to the 5th of x, and then we take the derivative of sine of x, which is cosine of x, and we do the chain rule, and that's pretty much all we got there. Number 9, part A, evaluate h of x equals the integral from 2 to x cubed of cosine t dt. So that would be, the integral is sine, and so, sorry, I kind of skipped a step. So sine of t, and we're going to evaluate it from 2 to x cubed. So we put in sine of x cubed minus sine of 2. Now part B is going to be to take the derivative of this function. So the derivative of h is going to be taking the derivative of this. So the derivative of sine cubed is 3x squared, which is the chain rule, times cosine of x cubed. And then the derivative of this part is going to be 0. If we didn't do all of this, we could have just done the fundamental theorem of calculus in order to get straight to part B, because the derivative with respect to x, the integral of 2x cubed cosine of t dt, that would be just cosine of x cubed, and then we have the chain rule, which is 3x squared. So we could have got that a shorter way.